Sorry?
Slide.
If necessary.
Can we get started, please? Before the evening's over, I would like to have everybody to sign the sheet back there at the table back there. So, do that, please. Welcome again to the 6th Annual Astronomy Lecture. Again, we have a parade of Iowa astronomers. This is the 6th one. And Dr. Marston from Drake University. Tony is not a full-fledged Iowan, and he comes from the UK. He graduated with his BS in 1984 from University of Manchester and his PhD in 1987 from the same university there. He has gained through the years several grants to write research papers in such areas of interest to him, namely Wolf-Rayet ring nebula and stellar evolution, circumnuclear emission mechanisms in safer galaxies, star formation and evolving stellar populations in ring galaxies, and X-ray properties of normal galaxies. He's done a lot of his work at Kitt Peak Observatory, National Observatory, west of Tucson, Arizona, and a similar observatory in Sierra Leone in Chile. Interestingly enough, Dr. Marston manages the Drake Observatory in Des Moines, so maybe he can say how often that is open before the evening is out, and you might want to venture down there. The public, I think, is invited most of the time. Is that correct? And he's made many presentations just like the ones he's going to be giving tonight, and the title of which is called Massive Stars. So without further ado, let me introduce to you Dr. Tony Marston from Drake University.
That's good. I'd like to get the applause over with to start with. You never know if you're going to get any at the end. As the Drake Municipal Observatory was mentioned at the start here, yes, we are open Friday nights, except for this Friday night. Being relays, we're not actually going to be open. I'm in Texas anyway. But other than that, we will be open for the next 5-6 Friday nights. If you want to come down to the Drake Municipal Observatory, it's that building that's on the golf course that you see north of I-235 when you're trundling through Des Moines. So if you've got a chance, pay us a visit, 8 o'clock Friday nights. We'll be going on through the summer as well. However, tonight what I'm going to talk about massive stars. When you look up in the sky, one of the things that seems to always come across is that you look up in the sky and it looks the same. Lots of stars, they're all in the same patterns, they're pretty much doing the same thing. I'm going to be talking tonight about some stars, though, that, at least in astronomical terms, are changing quite quickly. They're not always going to be the same. They are changing, and they're changing over the course of time, so that in certain cases we can even see them do some very strange things, including blowing themselves up. So if you like big bangs and lots of noise, these are the types of stars to be looking at. Now, when I say a massive star, what I'm talking about is a star that's basically going to be up to 100 times the size of our sun. So these are really enormous objects, and they're as big as we can get in terms of a single star in the whole universe. Let me explain what I'm going to try and do. I'm going to try and explain why we should care about studying massive stars at all. I'll talk a little bit about how massive stars change. I'll then talk about some very special stars called Wolf-Rayet stars, which I've been looking at for several years in my research. And in particular, what I'm interested in talking about is what they do to their surroundings. These are not very good neighbors necessarily. They mess up their surroundings and environments mightily. And in fact, one of the things that we can use is the effects that they have on things that surround them to work out what's happening to those stars themselves. So I'm going to try and work out the history of massive stars from what's going on around them. It's quite easy to do that in the similar way in your own home. If you see pizza on the wall, you know that your kids have thrown pizza onto the wall in their last half an hour to an hour before. We're seeing the same sorts of effects. These stars basically make a mess of their surroundings, and to what extent we can actually say how long ago they actually made that mess and what they did to do it, we can actually interpret what these stars were like in the past. I will also talk about some problems that we still have in trying to discuss this and why people are still studying these kinds of stars. So the first thing is, why should I want to go out and look at a massive star? I'll give you a couple of facts about them. First of all, there aren't many of them. Stars that are more than about 25 times the mass of the Sun actually are very few in our galaxy. We could almost number them. You can almost come up with a complete list. Now, there are 100 billion stars in our galaxy, most of which we do not take very much notice of. They're very dim, and they don't shine as brightly as our own Sun even. But these stars are enormously bright, and that's one of the first reasons for actually looking at them. So even though there may not be many of them, there's enough of them that they can even dominate the amount of light that we would see from an object like our own galaxy containing 100 billion stars. So we're talking about a few hundred or a few thousand of these things that can possibly outshine all the other billions. So they're interesting because of that. They're extremely bright and energetic. Why are they bright? Well, they're basically using up fuel. Things shine brightly because, stars shine brightly because they use up fuel. What fuel do they have? They have gases inside of them, and those gases are being used up very quickly in these stars' cases, and in this case, these stars last for millions of years. Now, a star like our Sun will last for 10 billion years. So it seems rather strange, but the bigger the star is, the shorter the length of time it actually lasts. So these stars aren't going to last for very long, but while they're around, they're extremely bright. Perhaps more esoterically, for those of you who've talked at all about things that are deep in space, Hubble has recently been looking at some of the deepest things in space. If any of you saw Mysteries of Deep Space on Iowa Public Television last week, they talked about the Hubble Deep Field, looking at things that are very far away, looking at objects far away in the universe. The reason we can see most of those is because they are filled with these very massive stars. And if we can understand massive stars, we can understand more about these objects that sit right on the edge of the universe. So I'm also going to talk a little bit perhaps about what they can tell us about the universe as a whole. Now, what happens to stars as they grow old? Well, basically as stars grow old, they change. All stars change. This is called evolution. It's stellar evolution in this case. Now, when we're dealing with humans, you evolve. You start off as a baby, you get born, then you're you go to school, you become a teenager, you go through mature years, and you age, and eventually you die. Stars do almost the exact same sort of sequence. Stars are born. They're sort of cradles of where stars are being born. They actually go through a sort of teenage phase. They get really disturbed and start blasting material out in all different directions in irregular tantrums. So they sort of go through a teenage phase. Then they sort of become mature when they sort of settle down a little bit and seem to do nothing very much for a period of time. And then they get old, and as they get old, they seem to perhaps get dimmer or change in color or texture, and eventually they end up dying. So they have a sort of similar sequence and to the way that humans actually change. Now, traditionally, when we're dealing with massive stars, and if I can get my worthy assistant to help me here. Traditionally, when we're talking about massive stars, it's been thought that massive stars will start out as large blobs of gas, which will come together and form eventually a very big star. Now, often astronomers like to use this diagram, and for those of you who are doing an astronomy class, and those of you doing the one in the community college, you'll know this diagram. It's called the Hertzsprung-Russell or HR diagram. You don't need to worry too much about it. We can basically put any star on this diagram we like. Any star you see in the sky, we can put onto this diagram. Basically, if the star is hot, we'll put it to the left. If it's bright, we'll put it at the top. If it's not so bright, it's down at the bottom, and if it's cool, it'll go off to the right. Now, the objects I'm going to be talking about are those white things up there. Stars that are white hot. They are so hot, these big massive stars, that they shine white hot, and they appear at the top. Because they're at the top here, this means they're incredibly bright. Not only that, they are going to be giants. They are giant stars. They are typically 100 or so times as big as the sun in size. Not just the material, but in physical size. They could start eating up that orbit of Mercury, and Mercury would probably not be able to exist in an orbit around one of these stars. Now, traditionally, people who've dealt with these stars have said, okay, well, what will happen when they run out of fuel? Will they always stay in the same place on this diagram? And the answer is we believe they won't. In actual fact, traditionally, we've always said they go marching across this diagram and become what we call red supergiants. Seems rather strange, but in actual fact, they puff themselves out. They puff themselves out because they keep on creating energy, not in the center, but just outside. And it's when they push it out now from closer to the outside, it's easier to push up the star and make it even bigger. As the star expands, the outer part becomes cool, and cool stars are red. If you don't remember anything else from this, remember this. Stars that are red are cold. Stars that are blue and white are hot. It's the complete opposite way around to the way that the artists do it. If the artists say a red is a hot color, it's not. It's a cold color. A star that is red is actually a cold star. The surface of these stars actually drops in temperature then when they get older. Now, all the time what's happening is that we're creating energy inside of the star by changing what the star is actually made of. So inside of these supergiant stars, we are continuously changing what they're made of. And as we do that, eventually you get to the stage where we can't change them anymore. So essentially what we are talking about are stars that sit at the top of this diagram. They're always referred to as supergiants, and they seem to travel all the way from being blue to being red stars, and then as they continue to evolve, they will eventually explode as they create iron in their centers. Now, there aren't very many of these. We reckon that there are probably somewhere in the region that they're about 1 million times as bright as our own sun, and only last perhaps as much as 1 million or 500,000 years. So all of this is taking place fairly quickly. And eventually, as I indicated, they will die, because what happens is that right in the center, they'll eventually form iron. And iron is as far as you can go in creating new types of elements inside of a star. And eventually, when you create this situation, the star will go boom. This is what every textbook you've ever probably, and that any of you will ever read in astronomy will tell you. At this stage, the star will go boom, it'll go supernova. This is what a supernova is all about. In actual fact, the star doesn't so much explode as implode. What happens is it can't create energy anymore in the center, and the outer parts are so heavy they just fall in on top of it, and as it goes crunch, this creates a huge amount of energy which forms a big shockwave which destroys the whole star as it goes out. So, this is what you're told about how massive stars change. However, over the last few years, last 10 to 20 years, we've started to realize that this probably is not necessarily true. Thank you for the slides. This is probably not necessarily true. Why? Because it turns out that stars don't just lose material, don't just lose mass. when they are going to explode. They don't just throw material out at that stage, but they do it all their lives. They're actually losing material all their lives. And in fact, they may never become big red supergiants, ever. They may actually become some other types of stars. And in fact, they may not even just end up over on the right-hand side and then going boom, but may even return to being big, bright blue stars. And a type of star of that type is what's known as a Wolf-Rayet star. Why do we think that these could possibly come from some of the most massive stars that we know? Well, first of all, these stars have been measured to have fairly high masses, about 10 or 20 times the mass of the Sun. Not the big 100, which is what the biggest stars actually have, but something like 10 or 20. They have lots of nitrogen and carbon in them. Now, nitrogen and carbon is not normal to have lots of in stars. The Sun, nearly about 99% of the Sun, is made up of hydrogen and helium. So these stars have somehow created nitrogen and carbon. How do you do that? The only way you can do that is inside of a star. So these must be stars that have evolved. They're old. They've created these new elements. So we've got lots of carbon, nitrogen, oxygen, and helium. All of these are bigger atoms than hydrogen and some helium, and this indicates to us that these are certainly older stars, but they're quite big. So they can't have been around for too long, because big stars don't last for very long, so they're not terribly old, but they are certainly older stars because of what they're made of. They also have what we call strong winds. We find that these stars actually are blowing. Now, the Sun does the same thing, solar wind. Every now and again the Sun has a big flare and everybody says, oh, watch out, we're going to have electrical shortages. In fact, an AT&T satellite went out the last time we had a big flare. It blew an AT&T satellite. An AT&T satellite would not be able to stand anything around a Wolf-Rayet star, because these stars are throwing pieces of material out in a similar way to the Sun, except much more powerful. So that means that they're actually losing bits of the star. There's a heavy mass loss. So what we seem to have now is a star that's on the wrong side. It's not red, and it's not about necessarily going to blow up. Or it might blow up, but we're not so sure anymore. Well, not only that, but it's not blowing itself up, it's sort of going at a more gradual rate. Yes, this is coming up fairly quickly, 2,000 kilometers every second, or if you like to put it another way, somewhere around 15,000 miles every second. Putting it in miles per hour, that's somewhere around 50 million miles per hour. So we're talking about things coming off very, very fast from the star. It's fairly energetic, but it's not blowing itself up. So these stars, it seems, don't necessarily follow the route that you've actually probably come across, or at least a number of you have come across in your textbook. There are a few other things that they probably do. And the answer to what they probably do is blow bubbles. Stars blow bubbles. And I like bubbles, basically. I remember a long time ago, I had a supervisor at my old university, and his son was not at all proud of him. He used to, whenever asked, "What does your father do?" he said, "He looks at bubbles in space," and looked very sheepish, and would actually sort of was never at all proud of his father because of that. However, bubbles in space happen to be very useful for us looking at these big stars. What do they do? Well, it's amazing. Space is, sometimes we say, it's a big vacuum out there. Well, it isn't a big vacuum out there. There's stuff all over the place. There's stuff in between the stars. It's called interstellar medium, and it's basically very, very thin gas. Now, what happens when the star is trying to push all of those fast-moving particles off its surface is it pushes away all of that gas, and it creates a big bubble. It sweeps it up, and it's a bit like using a broom. You come out with your broom and you've got dust on the floor, right? And as you push the broom, and the more that you push the broom, the more that material piles up. So the first thing we see is then that this star will actually sweep up material. However, it turns out that that doesn't seem to completely get rid of the material around these stars. So there must be something else that happens. And in fact, the new idea is that there is something else that happens. We create a sort of mini explosion in which we eject material off of the star at an even faster rate, but in bigger, heavier clumps. And this sort of forms another ring around the star. And then after that, we get even a third situation where we get another very fast phase of wind blowing into that material. So we have an interesting situation. Over a period of time, a star like our Wolf-Rayet stars, which are massive stars, will actually blow several sets of bubbles, one inside the other one. Now, sometimes these bubbles are going at different speeds and one can overtake the other one. However, essentially what we're doing now is that if we look at these things, we would expect in this new idea that we're going to form bubbles around these stars. So do we see that? Well, this comes from some work that I've been looking at satellite data. This is satellite data that NASA can get, that sends down to you. You can get it tomorrow if you want to. There's a service called Skyview, and all you have to do is get onto the internet, and you can get a picture of any part of the sky that a satellite has actually looked at, that NASA's looked at over the last 20 years or so. And this happens to be one of those images, and it shows a part of the sky in the infrared. And the infrared is part of what we can't see with our eyes, but you can with those special goggles that the Department of Defense gives out to troops for night sight. So if you had night sight, you could see this stuff in the sky. It's not something that you can see by just looking up into the sky, unfortunately. But what we see is that this is a position of where a star, one of these stars is, one of these big massive stars, and we can see clumps of material just scattered around it in almost a big circle. This is one of those big sweepings up of material that I talked about just a moment ago. We can see this in many places. Here's one that's perhaps a little bit more obvious, although it's quite faint. All the way around that cross is a position of material that's been swept up by an earlier stage of the star. Now, the thing about that is that you say, so what? It's sweeping up bubbles. It's sweeping up material, and yes, it can be quite pretty. We can get some really pretty looking objects, particularly if I start putting colour onto this. And you can get colour on your nice computer screen, and it looks very pretty indeed. But it tells us a little bit more than that. Because what we can do is that we can work out how long the star must have been trying to do this. And this is one of the sorts of things that you might want to know. How long is a star blowing these different types of bubbles that we talked about? How long has it actually been alive for? How long will it carry on for? And in fact, what we can do is make measurements of the size of these objects, work out how fast they're expanding out, and try and work out then how long they must have been doing this for. It's a fairly simple little calculation. The radius, or the size, divided by the velocity equals time. And that's just distance equals velocity times time. Many of you have probably done that. It's a fairly simple little calculation. If I know how fast these things are spreading apart, and I know how big they are, I know how long the star has actually been around for. So this is what I was talking about right at the very beginning. I said, if we look at what happens around a star, we can work out something about that star itself. And this is one of the things I've been trying to do over several years. And this is part of some work that I've been looking at, where we can try and look at the surroundings of these stars to work out how long they've been around for. So how long have these stars been around for? Well, the answer is somewhere between 0 and 10 million years. So this is one of those things that we can actually start to do by looking very carefully at just in a fairly simple way at some of the satellite data that NASA has given us. We can work out how long stars like this have lived for. Wolf-Rayet stars must therefore come from stars like those big 50 to 100 solar mass stars, stars that are much, much bigger than our sun, but are shrunken. They're shrunken. They've lost a lot of material over a period of time in those big, strong winds. However, that's one bubble. We can actually do better than that. We can get multiple of these things. We can get lots of them. So let's have a bubble fest. Here we go. Here's a bubble fest for you if this thing will actually, if these things won't fall. Various bubbles. Lots of stars with lots of material around them. In these particular cases, what have we got? We got two different stars here, and this material has literally been thrown off the surface of these stars. We can work out how much has been thrown off, and we can do the same little game we did before. We know how big they are, we know how fast they're throwing this stuff off. We can work out how long they've spent on throwing this material out into space. And what we find is that these stars go through different transitions. They last about 1 million years, sort of sitting there nicely up in the top left of a Hertzsprung-Russell diagram, very hot stars, very big stars, and then after a while they change. They change. We don't know quite what into. They go into something else, but we're not quite sure what. And when they go into that object, which could be one of the big red stars, or it could be something that's in between, then we actually find that they give out these big rings like this. And then after a while they change again. They become big blue stars again. And as they do that, what do we get? We get another bubble. In fact, this is the same star as that one. It's just taken with a slightly different colored filter. And with these different colored filters, I can see different things. You can see that this is a nice horseshoe-shaped object. This one seems to be much, much bigger. And it seems to be a sort of a shape of an 8. Why? Well, this basically means that the star did two different things at different times. This was probably formed after this one. So the star has gone through different phases, different parts of its life. And from this I can start to piece together what it is that these stars are actually doing. What they started with, how long they've been in these different phases, and what they're doing in those phases. How much material they lose. Are they going to become supernovae? Is there going to be anything left by that time? They're losing lots of material very, very fast. So we can basically show that these stars have lots and lots, and here's some more colorful rings around these stars, and lots of these big, massive stars have these things around them. And that's what I've been trying to use over many years now to try and gauge what these stars are doing. So the question starts to become, what are they doing? Well, it seems as though they are going through what I like to refer to as a 3-phase evolution. 1, they blow a huge, huge bubble. They can literally knock holes in your galaxy. They can knock holes in our galaxy. This is actually a huge, huge ring of material around a central object star in here. How much material has been swept up? 8,000 times our sun's mass. If we look carefully in here, and we look with optical telescopes instead of the infrared one, which took that picture, what do we see? We see something that looks like this. A big, huge, cobwebby mess of material, which is actually material and clumps and so on that have been thrown off of the surface of the star in, as you can see, a sort of kidney-shaped fashion. We reckon that there's something like 30 times our sun's mass in this material, and this come off of one star. That's a huge amount of material to come off of one star. Most stars don't even have that much material in them to get rid of. The cross marks where the actual star is, it's somewhat hidden in here. So it does that. It does this for about 100,000 years. It's throwing off this material for about 100,000 years. And then for about a few tens of thousands of years, something like 20,000 years to 100,000 years, it starts doing yet another thing. You see all of these big wisps of material out here. It's blowing even faster material that then plows through all of that stuff it threw off in the last phase. We have three things that this star has now done. A huge bubble, which is way out here. A smaller one, which is basically much like this. And now we see these things poking through here, which is a third one, which is going very fast and plowing through that material. And we now have what we call now a three-phase evolution for these massive stars. With all the material that they've lost and are continuing to lose, these stars are getting smaller and smaller. But they're still pretty dense. And there's good possibility that they are still going to be able to explode. In 1987, there was a big explosion in the star in a nearby object called the Large Magellanic Cloud. Unfortunately, you can't see it up here. You have to go down into the southern hemisphere to see it. And in that cloud, their star blew up and everybody was puzzled. Why was everybody puzzled? Because it was a blue star. Blue stars were not supposed to explode. These stars that I've now been talking about actually do seem to go back to being blue stars. According to all the textbooks, all the red ones explode. No, blue ones do as well. And these are blue stars, and they will continue to lose material, but as they do, they're shrinking, getting more and more dense, and as they collapse and implode on themselves, they can basically form a supernova. So these stars are now going to also form supernovae. They're going to form, and the surroundings to those supernovae are going to be these huge, huge bubbles. So, what have we got then as far as looking at these materials, and what more could we possibly get by looking at the surroundings of these really massive stars? Well, some of the conclusions that we've got here is that we have multiple shells that exist around these stars, and these are telling us clues to the past. This is what astronomers look for. Unfortunately, unlike most other subjects, we can't do very much about looking at taking a piece of a star and saying, let's chop it up and have a look what's inside of it. Let's do something with it, poke it in the lab. You can't do that with a star. You have to just take what you're given. And what you're given is the surroundings of a star, and from that surroundings, you can work out something about what it must have been like in the past, and probably where it's going right now. And these multiple shells suggest that these stars are going through different phases of their lives. Stars change, and these stars change rapidly. They spend a couple of million years blowing big holes, then 100,000 years throwing off material off of their surface, and then another couple of 20,000 or 30,000 years in which they start blowing that material that they've just thrown off their surface away. They're doing different things at different stages in their lives as they change. Now, at this stage you might ask, well, what's causing them to change? Why do they change? Why should they change at all? What makes them different in all these different stages? What makes them different is that they are constantly changing what they're made of. And it's amazing what difference that makes for a star. What a star is made of and how it's creating its energy are very important. Stars, as they start to create their energy, are constantly changing what they're made of. They're being made up of different types of material. And when they're made up of different types of material, you create energy in different ways. You can only make energy out of what's there. And if you've got different material, you go, oh, well, I'll have to use that, I suppose, instead of what I was using before. And that makes the star different. And as it changes, it goes through these different situations. Now, recently, we reckon that in actual fact, these three stages I talked about, maybe this is too simple even itself. Sounds complex, but in actual fact, even that could be difficult. Recently, I went to a a conference in which people are now reckoning that there is actually several explosions that occur, mini explosions that occur on these stars from one end of their life to the other end. And they send out it's almost like little smoke rings that get sent out every time they do that. Many little ejections that come out of these stars, that go out into the surroundings. So even what I've suggested may not be necessarily the whole story. What kinds of things are we trying to work out? We try and work out how long the star was going to be around for in these things by looking at their surroundings, how much material they've lost, how quickly are they losing their material. And also we're interested in what is their relationship to other stars that we know and are around us. So it seems as though in this kind of work that I've been doing here, when I was originally asked to give a presentation here, I was told, talk about what you've been doing. And then what I've been doing recently is working on this problem of trying to work out what it is that massive stars really do and what it is that they've managed to do to their surroundings. And basically the answer is they make a mess of their surroundings. Now, there are problems. There are still problems. We don't know everything about what these stars are doing. And here's just a few. Sometimes when the scientist stands up, I remember once being accused, you tell me that this is the way that these things work. How do you know? And the answer is I don't. And most scientists do not know everything that there is to know about these things. We probably know a bit more than you do because we looked at it for longer. But if you looked at it for as many years as I have, you'd know the same things. Essentially, we don't know the answers to all these problems, and we still don't know many of the things that you get told about on PBS programs. As an example, you'll be told that black holes exist in the middle of galaxies. There isn't one astronomer who can say that there is a definitive proof that that really is true. It is probably true. We don't know for sure. In other words, we don't know many things for sure. We've got best bets. So here are some of the problems that I've still got to play around with. I'm dealing with Wolf-Rayet stars. Where did they go? Where did they come from? Did they really start in the top left of our Hertzsprung-Russell diagram as massive stars which were white hot? Did they really change to becoming big red stars? I don't know that. They might not have got as far as being red. Maybe they got as far as being orange or green or something. I don't know. But then maybe there's something in between. How many explosions did they have? Did they have lots of them? Several? One? Did they just continue in much the same way that we see them now? It's probable that they haven't, because we see all these things around them that suggest that they have changed. How many stars do this? Do lots of stars go through this, where they're throwing off material left, right, and center? And how big a star do you have to be before you actually can do all of these kinds of things, these sort of astronomical gymnastics? And finally, is there evidence of multiple phases where the star is doing other things other than the things that I have talked about already? There are several suggestions that there are indeed more than the 3 phases I've even talked about that exist in the lifetimes of these stars. Now the situation is, if we don't understand this, and this is one of the problems that we have in astronomy, and this is a bit more philosophical than anything else. What we get told about what's at the end of the universe is based on what we know is around us. And we don't even know these stars that are around us. So how well are we going to know what's at the edge of the universe? I'll leave you with that question to ponder on it. If we don't understand things that are close by us, it's very, very difficult to actually try and work out what is happening, and indeed answer questions like, what is the universe doing? Where is it going to go? And is it ever going to come back again after this big expansion we seem to be seeing? So this then is leading to, hopefully, towards us being able to understand those objects, therefore, that are fairly close by to us, but they're essential to know, otherwise we can't work out what is happening to the objects that are closer to the edge of the universe. I wanted to end up here with one of my favourite images. I don't know that I've actually got it immediately to hand, unfortunately. So I may not end up with showing you. Yes, I have. I hope it shows up well. This doesn't look terribly exciting, but happens to be one of my favourite images because it's the first time that we've ever seen what's referred to as a big bow shock of material that comes around this star. And you can see all of those filamentary materials here. It's eating, literally eating into a big cloud of gas that's right next to it. And this is one of the first times this has ever been seen. So this is the kind of thing that we're now doing. This was actually data taken at the Kitt Peak National Observatory near Tucson, and it's using one of the new techniques of infrared imaging that we can now do from the ground. And you'll hear more and more of things like infrared imaging in the future because astronomy is going in this kind of direction. Different techniques to study the same things are now becoming available, so some of those questions are now going to become much more easy for me to solve due to the fact that we've got different instruments available for me to try and solve those kinds of problems, including now infrared imaging. Well, I think I'll probably stop right there, and I'm opening up to questions at this point. I'm probably going quite beyond my remit by saying, please ask any questions you want. I know I've been talking here about massive stars, but feel free, please, to ask any questions you like about what I've just been talking about, or any other part of astronomy. Yes, sir?
How old is the light that you're looking at in these WR stars?
Okay, the Wolf-Rayet stars generally are, these things are on average, they're about 6,000 light years away. That means that we're seeing these stars as they were about 6,000 years ago, on average. Some of them are closer, some of them are further away. But there are only about 200 of them in the whole galaxy, and when you realize that there's these billions of the stars out there, it's quite impressive that there's only about 200 that's actually been found. Shows you how rare they are, but they are remarkably bright as compared to other stars. But yeah, 6,000 light years away is the average for most of these, the ones that I'm talking about. You can find them in other places which are way, way further away, but these aren't. Yes, sir?
Are shockwaves thermonuclear explosions almost, or just shockwaves?
That's a good question. Are shockwaves thermonuclear explosions, or are they just basically things that come and splatter things out of the way? Generally speaking, the answer is they are things that splatter things everywhere in all directions. A thermonuclear explosion is just one form of an explosion. Explosion is an explosion as far as space is concerned. As far as space is concerned, whatever causes it, it's just a lot of energy coming out very quickly and trying to get out from there. And what a shockwave is when you try and make material go fast, so fast that it actually tries to go faster than the speed of sound. Now you hear a sonic boom from planes that go faster than the speed of sound. Sound does not travel in space instantly. If you see Star Wars, Star Trek, and everything's going and exploding everywhere, explosions do not make any sound in space. So stop the movie at that point or plug your ears. You should not be hearing anything. It's soundless in space. But if you try to go faster, too fast, the material can't get out of the way, and that's what's called a shock wave. And a sonic boom, when you hear a jet going faster than the speed of sound just overhead, and it creates that big boom, that's the same idea.
Question here. Can you show your last slide there?
Sure.
Or overhead? How do you determine that bow wave there?
Yeah. It's not the best reproduction. I apologize. How do I determine?
How do you determine that it's from that star and not the next one to it, for instance?
Oh, okay.
What kind of a thought process or measurement goes into
Oh, the basic measurement is that I know that the material that it's made of is at the same distance as that. When you look at a picture, you see two dimensions. You see everything. It apparently is just right there. Well, in actual fact, of course, there is some of that picture. Some of those objects are here. Some of them are back there. Some of them are way back. And most of that material there is certainly way back and is nothing to do with we see a big cloud that's off to the left here. So it's nothing to do with it. So we know that the distance of that cloud, and we know the distance of the stars, and there's only one star that could be close enough to do it. So that's the basic idea, that when you look through a telescope, you don't get a judge of how far away these things actually are. I remember somebody actually asking me, if I look through this telescope, how far away will it look? Well, it's still at the same distance. You don't physically move anything, and it's not really a case of you getting closer. It's like taking a picture and taking a photograph and enlarging it. That's what a telescope almost does. Imagine taking a photograph and you enlarge it. You haven't got any closer to the picture. You just made it bigger. So that's the way it will work. So in this case, we've got lots of objects that happen to be behind. And we know.
Is this simultaneous parallax that you're looking at
No.
to determine that it is a particular distance, or is it shots in different?
Oh, you're getting into very deep water there, talking about distances in astronomy. Please. I know. Distances in astronomy are a real pain. Distances in astronomy, if I want to tell you how far away something is, it's a very difficult thing to do. Parallax is the only true way of actually finding distances to any kinds of objects in the universe. It's the only true way of doing it. Everything else is a stepping stone from that. So in this particular case, knowing the distance to this, we don't know it that well. We know it well enough, but not as well as we would like. We do know that it's associated with the cloud, because not only is it roughly the same distance as the cloud, but it's also at the same speed. And the material in that part of the galaxy is moving at the same speed towards and away from us. We can measure speeds much more easily than we measure distances. But no, we haven't got a parallax to this. We do have a parallax just to one object that is a Wolf-Rayet star in our galaxy at the moment. Only one. Yes, sir?
How far is the closest massive star?
How far is the closest massive star? The closest Wolf-Rayet star that I've talked about here is I tell a lie. It's 800 light years away. That's the closest. There are not very many of them, so they're really scattered. They're really a lot, very, very scattered. The nearest star is 4 light years, so it's at least 20 times further away than the nearest of any type of star.
Can you explain the bubble part again?
The bubble part. Well, imagine that a star is able to blow, literally. And when you blow, you've got air coming out here. And the air is made up of particles, okay? And as it does that, the star then is throwing out particles from it, and that goes and hits material that happens to be around the star, that's littered around. And as it does that, it pushes it away, and it sweeps it up, and it basically makes a big hole. So it's just like you blowing into a paper bag, say. You blow out the edge of the paper bag, and it makes a big hole. And in this case, we're making a hole in space. Right at the back. How far is a light year? Good question. If you don't know these things, just ask. You've got to ask. Light year. 1 light year is how far light will travel in 1 year. Okay, now how fast does light travel? Does anybody know how fast light travels? Yes. Very good. 300,000 kilometers per second. Thank you. For those of us who still deal with miles, unfortunately, it's 186,000 miles in 1 second, or if you like to put it another way, about 5 times around the globe. So if you were able to go as fast as light, you could actually go 5 times around the Earth in 1 second. Now imagine that you were able to ride along with that light for a whole year. That's the distance of a light year. It's how far light will travel in 1 year. And I'll let you do that on your calculator, calculating how far it would be. 186,000 miles in 1 second, and there are about 31 million seconds in a year. Yes?
Is a black hole like
Is a black hole black? A black hole is actually not really black. A black hole is black because nothing comes from it. That's basically, the color black is a lack of light. In actual fact, it's a lack of light. If you're going to see any color other than black, you are seeing light. You are seeing something coming from that. Black basically absorbs everything. Everything that falls onto the color black just gets absorbed. Doesn't get reflected, it doesn't bounce off. So you see my shirt as being white because all the light that comes onto it bounces off and comes to you. Now with a black hole, when the light comes into it, it gets absorbed. Black holes swallow light, black holes swallow everything. You can't go fast enough to escape from the black hole. And if you've ever seen the Disney movie, you'll know what I'm talking about. You can't go fast enough to escape the black hole, and that includes light. So that's why the hole is black. Anything that falls into it just gets to disappear. You can't see light coming from it because it can't get out. So we get no light, and no light happens to be the color black. Sorry? Can you find the weight of a star? Yes, the answer to that is yes, but it's very difficult. And of course we can't use a big pair of scales, unfortunately. But there are ways of doing it. How do you weigh anything? How do we weigh the Earth? How do we know how much the Earth is, how much material there is on the Earth? Well, one of the ways of doing it is actually looking at objects going around other ones. So one way of actually working out how much mass we have here on Earth is knowing how long it takes the Moon to go around the Earth and knowing how far away the Moon is from the Earth. It's a calculation that has to be done using Newton's laws and Kepler's laws of gravity. So unfortunately it's a fairly difficult calculation, but yes, it can be done. And the thing is with stars, a lot of stars, you have one star going around another one. And if we watch them, we can see them pulling on each other. And how much they pull on each other and make each other go around in an orbit, one around the other, tells us how much gravity they have, and that depends on how much mass, how much weight they have. Is the North Star massive? Polaris actually is a fairly big star. It's actually quite a large one, yes. It's actually very close to being 1,000 times, well, it's certainly a few hundred times brighter than the Sun, so it makes it a big star, yes. But it's not what I would call massive. I only deal with very exclusive massive stars. Polaris doesn't count. It's not big enough. Not for me. Yes?
Do the bubbles in space ever pop or split open?
Good question. Do they ever pop? Do they ever blow up? Yes, the answer is true. Yes, they do. Because what happens? Well, eventually they run out of things material to go through. There's only a certain amount of space to go through before you run out. So what happens? The bubble runs out into nothing. It bursts. Yes, sir?
This is a little bit closer to home, but with the hail block comment, I assume you thought we could get a question on that.
That's fine.
The newspaper this weekend said that the third tale that science can't quite understand the sodium that they detected. Do you know anything about this sodium third tale?
I've heard about it. I know about the so-called sodium tail exists. Can I explain it? Well, I'm one of that group of scientists, I guess, so the answer is not really. However, I will point out one thing. A sodium trail has been seen once before in the solar system. And as you get a sodium trail that follows around the moon Io, which is the closest moon to Jupiter. Io forms what's called the Io torus around Jupiter. It's almost as though Io actually has volcanoes on it. It's the only thing with active volcanoes on it other than Earth in the whole solar system. These volcanoes are spewing out material left, right, and center. And as the moon goes around Jupiter, it leaves literally a trail of that material behind it. And that can be seen in the light of sodium emission lines, absorption lines. So basically, that kind of thing has been seen before, at least in part. It's not pure sodium, but that sort of thing has been seen, at least in part, in the Io stream of Io, the moon around Jupiter. That doesn't explain why it's in the comet, because I would not expect to see any kind of thing like sodium in a comet, which suggests that there's something very strange must have happened to that material and that comet earlier on in that we don't understand earlier on when it was made with the rest of our solar system. We don't know. I don't know. And I haven't thought about it long enough, to be honest. I'm lazy.
Marshall, let's
Yes.
go back to black holes for a minute. You told these young men right here that
Yes.
it emits no light. Okay.
Right.
How do we know that it's there? Can you explain to them?
How do we know a black hole could possibly? Well, this is, you see, this is the whole problem why we don't and why we can't say, why very few astronomers would actually stand up here and say, yes, for certain a black hole exists, because you can't see one. No one can ever see one. So how do we know that one exists? Well, there are three things that a black hole can have: spin, charge, well, we won't worry about that, it probably doesn't, and mass, material, mass. Anything that goes into it basically becomes its weight. And what happens is that then it will that mass, that material that it's swallowed, will be able to attract other material that comes nearby. So the stuff that hasn't fallen into the black hole yet, we can see it doing things like, say, circling around. It's like material going down the plug hole. It's like you've got a kitchen sink and you watch the water go down, it goes down the hole. You don't see the water after it's gone down the plug hole, but you saw the water swirling around. Why was it doing that? It was going around the plug hole. So you know a plug hole exists because you see the water swirling. Now, if you see material swirling around in space, around nothing, you possibly have a black hole. So one thing you can see is material moving around. That includes stars doing strange things in the sky, perhaps circling around. Another thing is that as this material goes around faster and faster around, it gets hotter. And when it gets hotter, that material gives out, in particular, X-rays. So there are two things that you can do to find a black hole. Find material that seems to be doing odd movements, and find it preferably giving out X-rays, because X-rays come out from very hot material. So that's one of the ways in which astronomers actually tried looking for a black hole. So you can't see it, but you can see other things being affected by it.
And there's some good candidates today for that.
There are some very good candidates today for that. Black holes come in different sizes, we believe, from objects that are about 10 times the mass of the Sun, or perhaps around that. And there's an object in the constellation of Cygnus. Anybody know the Cygnus the Swan? It actually looks like a cross, a big crucifix in the northern sky. Easier to see in the summer. In the middle of that is a big X-ray object which is called Cygnus X1, and it looks just like a big star that's sitting there in the telescope. But it seems like there's a big star going around absolutely nothing in space. And that's one possibility. And we also see objects which we believe are black holes which could be 100 million times bigger than the Sun, which sit in the middle of other galaxies, and these are sometimes referred to as quasars. And those objects we see material, or Hubble has now been able to see material apparently moving very, very fast around the edges of the centers of those galaxies. So there are very good candidates, but it hasn't been proven exactly. I think it would be very difficult for them not to exist now. I was trying to be as skeptical for as long as possible. I believe in what Carl Sagan said. Carl Sagan basically had a very useful little phrase. If you want to prove that something extraordinary exists, you need extraordinary proof. He was actually generally talking about things like UFO inhabitants, but basically it's the same thing. If you want something extraordinary like a black hole, you need very good, very, very good proof that it exists, because it's an unbelievably amazing thing if it really is an object that exists.
When
Yes,
the
sir.
bubble is forming, what exactly does it do?
Is that your question? What does it do? It just sort of hangs around. Actually, it gets in the way. Often what we find is that sometimes they bang into each other. It's almost like you've got lots of these bubbles floating around, and if you blow several bubbles you just go blowing bubbles around the place, you'll find some of them end up bashing into each other. And they sometimes coalesce. And one of the things that happens is there's so much material in these big bubbles as they get swept up, that as they bang into each other, they create new stars. So one of the things that can happen is that they crush each other, and we can create new stars out of the whole process. So another important aspect about massive stars is that they actually move all of this material around so that we can create new stars in the vicinity.
So I would imply that stars are being formed lots of places and not just in the middle somewhere?
Oh, absolutely. Stars get created all over the place, but only if you have gas. You have to have something to make it out of. If you don't have it there, you won't make anything out of it. So if you got nothing, you won't get anything. But yes.
Question? No more questions?
Okay.
Thank you very much, Dr.